Welcome to this STS session on high-speed testing. Today we'll focus on the high-speed test of mobile devices ranging from smartphones to tablets and other internet-connected devices like in the Internet of Things. So recent years have seen a tremendous evolution of smartphone technology, including high-definition displays and high-definition cameras, as well as very high bandwidth communications. And a lot of these advances in mobile terminals have been enabled by the introduction of multi-gigabit per second communication links within the device itself. So a small smartphone or tablet is essentially a network of highly interconnected components like storage or display or camera devices, and all of them are connected with high-speed gigabit per second SerDes technologies. So despite the drive to create very cost-effective and consumer-driven devices, the development and verification of these interfaces is becoming a rather big challenge because of the introduction of SerDes protocols. So one of the things that the industry has decided and has, to help reduce the challenges of development of smartphones, specifically the MIPI Alliance, the Mobile Industry Processor Interface Alliance, it has decided to create specifications and methodologies for defining the various links within a smartphone. So again, this picture on the right-hand side here is essentially the anatomy of a smartphone or a tablet. And as you can see, you have a major application processor in the middle. Then you have various devices like modems and RFICs, as well as the peripherals that really make the device look more and more like a high-performance computer. So mass storage, audio technology, Bluetooth technology, as well as all the sensor hubs that exist in there. So MIPI Alliance has went ahead and created the various standards for these links, and these are highlighted with the various colors here. One common theme for all of these standards is the introduction of low power modes, so to be able to maintain battery operation and mobile operation. A lot of these standards, as we will see, contain protocols for enabling low power or ultra low power or hibernation states. And what these mean from a test perspective is that they generally result in a lot more complex test setup than in conventional SerDes applications. When it comes to high bandwidth, of course, SerDes is introduced in the MIPI system because of high bandwidth. However, the high bandwidth transmissions and the high-speed transmissions occur in bursts. That is, they occur on demand. When the smartphone is asleep, there is no high bandwidth communication, and as soon as a user turns on the device or clicks on the wake button, then high-speed communication starts to happen. And again, from a test and measurement perspective, this results in also very complex test setups and specifically very complex protocol sequences that are required out of the testers. You need to be able to essentially emulate the notion of being asleep and then waking up and sending high bandwidth data and then going back to sleep again. And then the last challenge is that, of course, these applications are driven by very high volume, which at the same time means very rapid time to market. So we're seeing tremendous shrinkage in the time it takes to create a new technology, define it, specify it, and then actually introduce it into product. And part of the ability to create such rapid introduction time or time to market is really a big expense on the capital side, where a lot of capital equipment, a lot of tools are acquired to very rapidly create these solutions. So in today's presentation, we'll talk about some of these challenges from a test and measurement perspective. We introduced the background of the mobile trends and where high-speed SerDes is being introduced in the mobile phone. And now we'll get into a little bit more detail on this concept of low power versus high-speed operation mode, which is really the mainstay of mobile terminals and of high-speed communications on mobile terminals. And so we'll describe some of these concepts at a high level, and then after that we will use these concepts to define the requirements for testing transmitter devices. In other words, if you're a CPU manufacturer and trying to test how the CPU sends display signals to the display driver, then these are the transmitter tests that you are interested in. At the same time, after that, we will describe receiver tests. So if you're a CPU manufacturer and you want to see how your CPU reacts to signals coming from the camera interface or from the sensor interface, then you are looking at receiver tests. And then finally, you introduce some validation solutions as well as production test solutions that exist out there, and that certainly Introspect Technology is a big part of. So the concepts of LP and HS communication are described here, and essentially any MIPI standard or any standard that's really driven by mobile interfaces will look like something like this. It'll have the following general state diagram or timing diagram. It will include a low power state to conserve power, as I said. So these are states that actually can remain for a very long time. The vast majority of time the mobile terminal will be in this state. So 95% of the time or 90% of the time it will be in this low power sleep state. However, what is key to the ability to create a high definition user experience is to very rapidly transition from this low power state to the transmission of high-speed data. So transmission of high-speed data is highlighted here in the blue section, and in order to go from the white section to the blue section, a very specific sequence of events is required in order to prepare the system basically for transmitting large amounts of data. And so we show this with the pink section here called preparation or prep for high-speed data. And then some demarker in orange here, some marker that says I'm starting HS data right now, right this moment. Then the HS data starts. Then at the end of the HS data, a marker is generated that says, okay, I'm stopping the transmission now. I don't need to transmit any more data, and I would like to go back into low power state. So this would be the end of the transmission state. And so the key really is how the transition happens from LP to HS here, from the low power to high speed, and then also from HS to LP, from high speed to low power, right at this very end. And as we say in the second to last bullet here, is that there are very strict timing requirements that are imposed by the standards in order to help interoperation, and these will be described briefly in the next few slides. And then finally, I described here a very basic concept of low power and HS modes. However, different standards, and specifically different standards in MIPI also, define these transition states very differently. So in the next 3 slides, I will show 3 examples of 3 different MIPI standards and how they take this general big picture view of transmission theory into a specific application and specific implementation. So in this slide, we describe this concept of low power and high speed for D-PHY standard, for the D-PHY standard. And so these items are displayed here in this slide. And I tried to use the same color code that I did for the previous slide so that it can be, we can relate to it. So the black section is the low power mode. And in D-PHY, low power transmissions happen using LV-CMOS single-ended signals. So this is like going back 40 years in time and having very low technology, low speed communication based on single-ended 0-1 signals. And so that's the LP state at the left side here, and then at the right-hand side here as well. To transition to high-speed state and to be operate in low power, we, as you can expect, high-speed state often exists in differential data. So eventually high-speed transmission will be in differential plus minus data. But we need a specific transition event to help the receiver understand that high-speed data is about to be produced. And so this is done in D-PHY using a specific sequence events in the LV-CMOS signal. So the CMOS signals, 2 wires of the CMOS signals start at the 1-1 state. They start high, and then one of them goes low, so that's LP01 state, and then they both go low to the LP00 state, and then the differential transmitter starts to play a constant 0 signal. So this is all described in this red section here. And so presumably after this set of events that I just described, the receiver will be ready to accept differential data. And as you can see, there are specific timing requirements here as well. At any rate, after the preparation time in purple that we show here, we want to send a marker that says HS data is really starting now. And so that's the orange section. And in D-PHY, this is signified by a single word that's called SOT, which means start of transmission. So that's a single byte of data basically that says the transmission is starting. And then in the blue section here, basically the payload data is being transmitted. And what I describe here is that it's transmitted as a source synchronous data with a clock. So there's a clock lane playing, and then the data is clocked. For every clock tick, there's a certain bit of data that's being transmitted. And then at the end of the transmission, a marker is introduced by basically having a constant value of differential signal, followed by a 1-1 transition. So both LP signals go to 1-1 at the same time. So that's D-PHY. The next slide is M-PHY. And again, very similar concepts. Like I said, the high level is the same, except that the base technology is different. And what has M-PHY decided to do is slightly different. M-PHY decided that the black section, the low power section, will still be differential mode, so it'll still have a plus-minus differential pair transmitting data. However, transmission will happen using pulse width modulation, which is again a very old communication technology from 40 or 50 years ago even, and it's very, very slow. So to conserve power, it's still a differential pair, but it's a very slow differential pair. And then to enter into high speed, then the differential pair will change polarity from 0 to 1, but it's still a differential pair, and then it will stay 1 for a while, and then still in the purple section here, the transmitter will send very high frequency data, a very high frequency pattern, and that's called the sync pattern. So this is a very high frequency pattern that's really used to tell the receiver that now high speed data is about to arrive. And then after the sync pattern is generated, a marker called MK0 is transmitted to say that the high speed data or the payload data is about to start here. So the receiver is expected to listen to the payload data in this section here and nothing else. It's preparing to receive the data in this section, but it's receiving the data here. And the reason that the M-PHY standard requires a very high frequency sync pattern to play on the left here, unlike D-PHY, is that in M-PHY there is no clock signal. So M-PHY operates based on CDR, on embedded clock. And so because it operates on embedded clock, for it to reliably receive data in this section here after marker 0, the CDR has to train. And so we need to give the CDR enough time to train on the incoming data before producing the data. And so that's really why the sync pattern exists here. But at the end of the day, measurement or acceptance of data, reception of data, only happens in this blue section. At the end of the transmission of data, a certain kind of marker called marker N, and marker N really depends on the kind of transmission being produced. It could be a marker 1, marker some other marker, but it basically gets transmitted, and then the device gets into the black state again, which is the stalled state. So it's still differential, but very low frequency. So difference between D-PHY and M-PHY is that D-PHY in high speed is source synchronous, whereas M-PHY in high speed is embedded clock or based on CDR. Finally, we show the latest standard from MIPI. This is a brand new standard that was just released a couple of months ago, and it's called C-PHY. So C-PHY is similar to D-PHY in many respects. The black section, the LP section, is LVCMOS, but instead of 2 wires, there's actually 3 wires, 3 wires of LP data. And that's the LP data on the black sections here. Preparation to go to HS happens in a very similar manner to D-PHY. So the LP data goes from 111 to 001. So 2 wires go 0 and 1 wire stays high. And then to 000, all wires stay low for a while. And then unlike D-PHY though, the high-speed transmission is really completely different in C-PHY. And we'll describe it in the next slide. So instead of sending a constant value of 0 as in D-PHY, the C-PHY standard transmits a constant stream of symbol 3. So many values of 3 are being transmitted in preparation for the HS data. And we'll describe the concept of symbol in the next slide, but it's completely different from binary communication, and it's more like RF communication. At any rate, after preparation, after training basically for the receiver to start listening to the data, the start of transmission is signified by a single word like D-PHY. However, it's not called an SOT, it's called sync word. And sync again is used to help the CDR in the receiver lock onto the incoming data. And then the blue section is the payload data itself. So this is really the data that the receiver will listen to. Everything else is just preparation for it. And as I'll say here in the bottom section, the data is not source synchronous and it's not embedded clock like in D-PHY and C-PHY and M-PHY. Rather, in C-PHY, the data is what is called three-phase encoded. So it's a special encoding scheme that does not require a clock and that is similar in concept to how symbols are transmitted in RF communication links, for example. After data is transmitted, the post segment is transmitted. So this is basically the end of high-speed transmission is signified by a constant stream of symbol 4. So start of transmission is signified by a constant stream of symbol 3, and end of transmission is signified by a constant stream of symbol 4, and then we get into LP. So we described the three-phase encoding briefly, and its high-level picture of it is shown here. The idea is that we start with different digital data, binary data, 16 bits of data as before. However, these bits are basically mapped and encoded into symbols, and there's 6 possible symbols basically that are available, 6 different states that the actual wires on the PCB board will have, and these basically allow us to transmit higher bandwidth data than binary data. So it's really the concept of symbols, and the way that data is transmitted is basically through transitions on a state diagram, very much like in RF. So there's 6 states here, plus Y, plus X, plus Z, minus Y, minus X, minus Z, and data is transmitted based on transitions, whether clockwise or counterclockwise on this state diagram. The net result of it is that we get higher bandwidth, yes, but it's generally difficult to actually recognize what any instantaneous value of voltage on the wire really means, because it's really non-deterministic, and so it's not straightforward to visualize waveforms on an oscilloscope the way one is able to do it with binary data, for example. But the concept is based on high, RF kind of signaling. So with the above introduction to all 3 standards, we went through LP to HS in general, and then we described how it's applied for each of the 3 MIPI standards. Here now we'll get into the transmitter testing requirements, and most of the time we'll use C-PHY as an example, just because it's the most recent one and because it really shows the concepts very, very nicely. So first is the low power operation, right? So low power in HS really means that any communication link will sometimes operate in high impedance state or in low impedance state. And so this is shown in this block diagram here, where there's resistors that could be turned on and off, and these are turned on and off dynamically in a system. So from a test and measurement perspective, when we are testing a transmitter, for example, we have to give the transmitter the same conditions. When the transmitter wants to send LP data, the tester has to disable its termination resistors and look like high Z, so that the data comes in and goes into the LP receivers. And so that's really what we're saying here, is that the tester needs to have integrated termination that is dynamic. And this helps eliminate the need for high impedance probes or external boards that could be used to emulate this function. So that's the first requirement generally for testing mobile devices in the new age. The second requirement, again, when testing transmitters, is to track burst mode operations. So we described how really the data happens in the blue section, right? And really, that's really what matters, and that's where we need to check that the data was transmitted correctly. So from a digital validation perspective, the data that matters is here. From an analog perspective, everything else matters, the timings matter, and this will be the subject of the next slide. But from a digital perspective, this is really what matters. And so this slide here shows the example construction of the C-PHY packet, as I mentioned before. And we're showing that really the tester needs to be able to decode and detect this data in the blue section here as the first and foremost requirement before anything else. Now, from an analog perspective, as I said, we need to also know the timing of these events, when the signal will go from LP to HS. And this is what we're showing here in this slide, again in the context of C-PHY. To check the data for pass-fail checking, we just simply need to look at the payload data, and that's what I described in the previous slide. However, one of the very important parameters of low power and high-speed transmission, as I mentioned, is the time it takes to go from LP to HS, and that, does that fall within spec or not? And that's critical for interoperation from various vendors. And so in this view here, we show how we would like to detect the various transitions, from LP, in the case of C-PHY, where there's invalid symbols, and then after LP, right away, the transmitter starts to send the 333 stream, shown here. And again, as you can see here, that the wires themselves, the differential data is changing all the time, but from a state diagram perspective in C-PHY, the symbols are all 3. And that's why it's difficult to look at the waveforms on an oscilloscope and decode the data. You really need to go decode the numbers at the bottom section here. At any rate, we see that this is the duration of the 333 preparation period. Then we see the sync word and know how long it took for the sync word to arrive, plus the data. So we went from termination control to looking at the payload data only, and then finally looking at the global timing parameters basically out of the MIPI link. And then the last topic for transmitter testing is that high-speed MIPI standards and mobile standards in general, because they are based on SerDes and because of the very high data rates that are sustained, have now also introduced the concept of BER testing, just like on conventional SerDes technology like PCI Express or SATA. And so one of the things that the MIPI standard has is BER testing, and this is an example of how one can perform long-term BER tests. In this case, we run 10 hours of BER tests just for validation to make sure that the link is valid. What is truly special about MIPI, though, is that this BER testing is done in burst mode. So when the signal is being transmitted with LP and HS in it, the BER tester is required to ignore all the LP data and to track the beginning of the burst mode data and measure its BER. And so this is what we're showing in this slide here. We now go on to the receiver test requirements. So similar to transmitter testing, in receiver testing we want to be able to guarantee that the receiver will operate under realistic testing conditions. So it's not just nominal conditions, but realistic testing conditions. So a lot of what is talked about in receiver testing is really stress testing. And in this slide here, we talk about the stress testing related to the transition between LP and HS. So I had said before that data goes in LP, which is a high level, LV-CMOS level. Then we go from 1,1 to 0,1 to 0,0. And then some small differential signal is being transmitted in high speed. So that's the concept. However, as you can imagine, if the LP voltage is too low and the HS voltage is too high, then there could be contention and there could be problems in reception of data. So one of the things that we look for in receiver testing is to stress the receiver as much as possible and to ask ourselves, what is the smallest low power voltage that the receiver will detect reliably before having errors and before being unable to detect proper communication. In other words, before it gets confused between the LP and HS signal. So that's the LP mode testing, and it can happen on the LP high level, as I show here with this sweep, or also it could happen on the LP 0 level, as which is not shown here. It's just shown as 0 volt here. Similarly in HS, again, same concept. In realistic system conditions, maybe there is just a ground potential between the transmitter or the receiver, or there is voltage offset, and so it could be that the common mode voltage on the high-speed section now could be too low or too high. So this is the same signal as before, LP high, LP11, LP01, and then LP00, and then high-speed transmission occurs. And what we do in the tester when testing the receiver is we keep pushing the high-speed transmission from a very low value, even negative value, all the way up to a very high value until the device fails, until the receiver fails to see high-speed data. And this again allows us to clarify the distinction between LP and HS transmissions, as well as understand the margin in the receiver and how tolerant the receiver is to realistic system conditions. Very similar concept, and perhaps just a slight elaboration on it, is that, again, because of the mobile nature of the terminals and the very low-cost nature of the power regulators and the power supplies and the PCB material and the decoupling capacitors, it is actually quite possible that signals can go negative in voltage, and the receiver is supposed to tolerate this. So what we're showing here in this slide is simply an example of the sweep of HS data that is, goes from here, a negative value. There's about minus 100 millivolt of voltage being applied here into a receiver, and then it's swept up to now a positive value where there's more than 200 or 300 millivolt being applied into a receiver. And so that's really been a key parameter for testing of mobile terminals, whether it's D-PHY or C-PHY as well. And then the other item that's really extremely important for receiver testing, and it's one of the most important tests actually for receivers in high-speed standards, is the jitter tolerance test or the jitter injection test. And the reason for this is really described here very simplistically, is that nominally a receiver is expected to pass 0 BER with normal signal conditions. So the signal on the left here is just a normal signal. In this case, we're showing a C-PHY, but you can see some, sharp transitions. Signals stay high for a long time before transitioning, and so there's a big black area for decision making in the middle here. And so typically a receiver is expected to operate under this condition. However, in realistic PCB traces on small mobile terminals where the PCB traces are very thin and narrow and the PCB material is very low cost, then the bandwidth on these PCB traces is low. And what this means is that the signals, by the time they reach the receiver, have a slower bandwidth. So you can see the waveforms are more smooth. There is inter-symbol interference. There is slightly more jitter on the signal. And so the decision area in black is reduced. And so the receiver is required to be able to tolerate this kind of loss. And that's why, from a test and measurement perspective, the tester has to be able to stress the receiver and reduce the bandwidth as well. And then finally, there's other sources of system noise that exist on a mobile terminal when there's, there's interference, there's EMI, there's power supply noise, and so on. So in addition to bandwidth reduction, we also introduce jitter injection as well to close the eye even more. And so typically receiver testing will start with a clean eye, then we will start to close the eye more and more, create a closed eye that is prescribed by the standard, by the MIPI standard. And once this closed eye is created, this closed signal, this stressed signal, is transmitted into the receiver for testing it. And then the final parameter for receiver testing that is required is skew injection. And skew injection is necessary again because of PCB traces. So in this picture here, we show how certain channels on a PCB system could have different trace lengths. So we have the driver, three differential pairs out of the driver, let's say on a D-PHY driver, and then 3 differential receivers. The receiver only sees the signal here. So even if there's a perfect transmitter D-skew or transmitter skew between the 3 lanes, once the signal goes through PCB traces, it will see, each receiver will see a slightly different delay. And so we show here the blue signal is very late. It's a very slow PCB trace, long PCB trace. The yellow signal is a bit slower, and then the green signal is much shorter. So green arrives first, followed by yellow, and followed by blue. And so from a test perspective, again, the tester is required to inject arbitrary amount of skew on each data lane independently. So we have shown the basic requirements for transmitter testing and receiver testing, and here we will briefly just show very brief tools, the tool trends basically for validation and production testing. And so the first trend that we've seen is basically an automatic approach to validation. The amount of data that needs to be collected on these devices is very immense because of the various modes, the LP modes, the HS modes, as well as the number of lanes. And so the traditional paradigm of just having, very simple tools is no longer valid, and now we're seeing a drive towards very automated software-driven tools, as we show on the left-hand side here. And so from a bench perspective, here's an example of a D-PHY validation setup. And again, so the tester is quite compact here in this case for D-PHY. This is a tester from Introspect Technology, and the software interface for it is very compact. Parameters are defined at a high level this way, and then automation is achieved with the Python programming language. And what we've seen in our experience that there's about a 5 times reduction in test time when using this approach to automation versus conventional tools. Similarly for M-PHY, the setup is very similar, again, as V1C tester, differential tester, used to connect to devices and able to perform tests based on a software environment. And finally, this is an example of a C-PHY validation setup, where again, the tools typically consist of a generator, and there is an analyzer, 2 testers here, software tools, and then some scope for verification as well. And then finally, for production testing, there is a big trend in the industry right now to try to take legacy ATE, legacy LSI testers that cannot do gigabit per second, and then apply BOAST modules on them to be able to do multi-gigabit per second testing. And so we've seen this for MIPI, we've seen this for other interfaces like DisplayPort or HDMI as well. And so the BOAST module sits on the load board just like any other device and is controlled by ATE pin electronics. So the advantage of this, of course, is the size and cost benefit. So many sites can be tested with very compact BOAST modules. And then, of course, the characterization capability is now very similar between the ATE and the bench. So at Introspect, we focused very heavily on high-speed SerDes testing, specifically for the mobile age. We have spent a lot of years developing solutions for ATE on the right-hand side, as well as for the bench. And we've come with solutions that basically bridge the gap between the low-cost, high-volume ATE and the very high-performance but low-volume bench tools. So we have spent, invested effort in creating automated scripting-based solutions that allow for testing of MIPI interfaces both from a receiver perspective and a transmitter perspective. So in conclusion, we have described the mobile interface industry in great detail and showed that how the MIPI Alliance has really created standards that help proliferate high-performance computing on mobile terminals like smartphones and tablets. These standards are terrific in what they could achieve. However, they do require new test requirements, and we went through some of the new test requirements in this presentation. For example, on transmitter tests, MIPI standards or high-speed standards targeting mobile terminals in general require dynamic termination, require the ability to track burst mode operation, and to track global timings associated with low power and HS transmissions. And then on the receiver side, of course, any generator that's testing a receiver has to be able to generate LP signals as well as HS signals, and has to be able to provide voltage stress and timing stress on both of these parameters. And finally, we described some of the solution spaces that exist today, specifically ones from Introspect Technology on the validation side, as well as on the production testing side. Thank you very much for your attention.